So there's no lecture on Friday. All right. Today we're going to talk about filtering. And to begin with, I'll just show you a demo of some simple filtering in order to sharpen an image. So here I've written this code in MATLAB. It reads in a demo picture they have. It's this rice picture here. Okay. There's a nice simple black and white picture of rice. Now, what I'm going to do is I'm going to blur this image as if the camera moved while it was taking a photo. Okay, now a good model for that is that you have some blur impulse response that's convolved with the image. This is actually a pretty good model of motion blur of the camera. Okay, because how should I interpret this blur impulse response? That means had you tried to take a picture of just one bright pixel in the center, it would have been so blurry it came out like this. Okay, that's how we should interpret the impulse response, right? An impulse in for a two-dimensional signal is just 1 at 0 at the origin and 0 everywhere else. That's white with black around it. Okay, so if that's what a star looks like in our picture, then when we take the picture of this rice in that way, we get this one. It's blurry. So there's our blurred image of the rice. I hope the projector is good enough that you can see the difference. You know, it's a little bit better when you see it directly on the computer screen. But okay, so this is blurry a little bit. And the point is I want to make a filter that sharpens it. So if this is all I'm given as the blurry one, I don't have the original, can I filter it somehow and get something that looks a little sharper? Clearly these capabilities are in software like Photoshop. They have all sorts of algorithms to try to sharpen things. And I'll show you a very simple method. If I have some way of measuring what the blur impulse response is, then I can come up with a sharpening filter based on it. So here, what we have here is the two-dimensional Fourier transform of our blur process. So here's the impulse response in time. If I do a two-dimensional Fourier transform and just plot the magnitude here. This is a plot of the magnitude of the Fourier transform. The center is frequency 0. Okay, I've centered it with FFT shift. So what this is saying is 1 means those are parts of the frequency domain that are kept, that are passed through this filter, that aren't eliminated. Now black being a value of 0 means that frequencies, those frequencies are, attenuated, maybe deleted entirely from our image. So what we see, for example, horizontally, we see that quite a large range of frequencies are kept, even when we do this blur. And the reason for that is that if you look at the blur here, it doesn't blur as much horizontally, right? So since it didn't blur very much horizontally, ideally, this would be white everywhere. If we had no blur, this would be white everywhere, an all-pass filter, okay? But because of the blur, it cuts out some of the frequencies. But we see that happening more in the vertical direction because it blurred more that direction. Okay, so that's how you should interpret this. Each of these, you're used to thinking of Fourier transform of a one-dimensional signal and what the frequencies mean. You have to kind of bend that intuition to 2 dimensions and think about what frequencies mean. Like a frequency in this direction is a wave that has pretty quick cycles, short periods, pointing in that direction, a plane wave. Okay. All right, so now that we know that this is what our blur did to the image, then we would want to undo it. We know something about how to do the inverse of a filter. In the frequency domain, it's very simple. You just take 1 over this frequency response. Okay, so let's design a filter that does exactly that. We take the inverse of this. Now, if you look through my code, and you can look at it later if you want, I don't just take an inverse. I basically do an inverse, but here's my deblur filter. You can see there's some sort of inverse going on here, but you add a constant into the denominator of your inverse. In real settings, you always assume that there's some noise in your image process. And if you do an inverse without putting that constant in the denominator, there's a possibility that you'll blow up the noise in certain frequencies where the frequency response was very low. You'd have a very high deblurring filter. and you could just get a lot of noise that way. So actually, under certain stochastic models, if you add a constant in the denominator, that's actually the optimal way to estimate the original signal. Okay, so that gives us a de-blur filter that looks like this. So here's the impulse response that we calculate for a de-blurring process. Let me put up both impulse responses next to each other. This here was the impulse response that caused the blur. And this here is going to be what we apply to the blurry image to try to de-blur it. Looks very crazy. Right? It's got a lot of high frequencies in it. But if I take this and I do a convolution of this with my blurry image, pull up the blurry image again. Here's the blurry one. I'm going to do a convolution of these, and I'll plot the result, and we'll hope it looks like a de-blurred image. So there's the result. Okay, here was the blurry one, and here is the de-blurred image. Okay, so a question was, what's all the stuff on the top? And there's some stuff on the bottom too. So well, first of all, let's recognize that the middle looks pretty good, right? This looks like a de-blurred image, so it worked very well. But actually, when it was blurred, some information got lost because we have I'll put all three. Put all three images up here so you can view them. Here was the original. Original here, blurry here, de-blurred here. The original, of course, does not have those lines up there. But notice that when you blur, some of the picture gets kind of smeared off of the off of the camera's sensors, right? So there's no way to completely undo the blur process. You're always going to have things that leaked off the edges. And that's kind of how you can understand these ripples here. It's sort of like the artifact that's caused by your de-blur filter because it can't reconstruct these parts because some of the information leaked off. Okay, so that was just an example of designing a filter for some purpose that maybe is a little more concrete, since we tend to stay very general. Okay, let's go back. Let's discuss filtering. So filtering basically is design a system, and often it's going to be LTI, and since we're really learning to understand LTI systems in this class, let's just specify that we design an LTI system to behave a certain way. That's basically what a filtering is. But usually, your design involves the frequency response. So you have some particular frequency response in mind, and you want to design an LTI system to have that frequency response. Or another name, a particular transfer function. So this is usually the starting point of designing a filter. You have some frequency response in mind. You want to design something for it. Now, first we'll consider a low-pass filter. But you'll notice that we have a lot of emphasis on low-pass filters. We've talked about them many times. So I guess I might say, why an emphasis on the low-pass filter? Aren't there many other filters we care about? And here's one good reason. You can build, for example, a band-pass filter out of a low-pass filter. So if you have a good design for a low-pass filter, then let's see how you would change it to get a band-pass filter. Does anyone have an idea? In fact, you could think of what's your idea? Like a high pass and combine them together. Yeah, you could do that. You could do like a low pass followed by a filter that has a high pass filter. So that's one way you could do it. And then we just have to say, how do you do a high pass filter? Very good. You can do it through subtraction. So we'll do that in just a moment. That's a great method. And there's even another way that does not require two filters in a row. If we think back to the convolution rule, the modulation rule. Suppose you have some low-pass filter like this with an impulse response, and suppose you multiply it by a cosine, so you just modulate it. Okay, then this, of course, is going to be convolution in frequency. And so what that means is if your low-pass filter looks like this, let's say it's not ideal, something like this. Okay, this is your h of f. And, of course, the cosine looks like two delta functions, one of them at f and one at negative f. And the heights, of course, are just a half, but it's not so important. Then you notice that assuming f is much bigger than the cutoff of the low-pass filter, you're going to do a convolution of these. And so the result is you'll get this. Whatever. That and that. Okay. At frequency, centered at the modulation frequency. Now, this is not necessarily any better than the idea that was just suggested of doing a low pass and a high pass. It's nice that there are so many different ways to interpret. Well, once you're comfortable with the Fourier transform properties, there's many different ways to design and to interpret designs. Okay, so let's talk about the high pass filter because it was suggested maybe you do some sort of low pass and a high pass to get your band pass. Okay, well, a high pass filter can be constructed just by doing a 1 minus your low pass filter. Okay. Now, in the time domain, that's in the frequency domain, right? So what we mean is we want something like this. We want to to cut off parts of the signal at too low of frequencies. So we want a frequency response that looks like that type of a thing. Ideally, it would just be a sharp threshold. And notice that if we did 1 minus our low-pass filter above, we'd get something like that. There would be some ripples here. Okay. But it would be a high-pass filter. In the time domain, this is delta of t minus h of the low-pass filter of t. So basically, yeah, we just let your signal through and subtract from it the low-pass filtered version. Okay. Now, let's talk about some of the methods of designing digital signal processing. Okay. So digital signal processing, often abbreviated DSP. There are a couple of very common methods of implementing a filter here, and they're usually referred to as FIR, which means finite impulse response, and then we have another one, IIR, which you can guess means infinite impulse response. Has anyone heard these acronyms, FIR? Actually, sometimes I read, I think I read a Dan Brown book where he was throwing out jargon to sound sophisticated, and he said there was an FIR filter in there. All right. So the way that you implement an FIR filter, let me throw out a design that's a very common design for some signal processing, and we'll see why this is a finite impulse response filter. Suppose you have samples from some you have some real-world signal that's going into your DSP processor. You can think of it as sound or whatever's being measured, right? And it's coming in sampled already, okay? So you have xn as some input. Well, you have some memory units. I'm just going to represent these as blocks with a D for delay. that's going to hold on to one sample for one moment, and out of this will come the sample that was there in the previous time step, n minus 1. Okay. Now let me have a series of these delay elements. I'll just draw 3 here. So what that means is we're holding on to 3 samples of the past. We're getting new samples all the time, and we're just retaining in memory 3 of the past samples. They're going through this block diagram. So this is x of n minus 2. This is x of n minus 3. Okay, so when a new sample comes in, it kicks the old one out of memory. All right. This is actually, in real life, the way that DSP processors work is they have some memory. It's longer than 3, some amount of bits that are a buffer. They read in samples, and as they cycle through the buffer, and they overwrite the old samples. Okay. Now, suppose that you're going to produce some output in the following way. You do these arrows. Let those be amplifiers. Okay, they're just going to scale multiply that signal by a constant number, and I'm going to label these constants. I'm going to draw this big. This is going to be, well, we'll see. I'm going to start at this end, labeling. Conveniently, I'm going to label that h of 0. I'm going to label that h of 1, h of 2. Whoops, that's n, not 2. H of 2 and h of 3. And out of these, I'm going to just add them all together. I know we don't use block diagram notation that much in this class, but I expect that this is pretty straightforward what this means. It means the processor is going to take these different stored values. It's going to do this multiplication, add them together, and use that to produce yn. So at each time n, it's sort of averaging the past few samples of x. We can see that this is a convolution. This is a linear time invariant process. And in fact, we can see that I've even conveniently labeled those amplifiers with h0, h1, h2. That's the impulse response, right? So y of n actually equals xn convolved with h of n, assuming h of n is just has 4 non-zero values here. These we call the filter taps sometimes. Okay? So a simple implementation of doing a convolution, which is a filter. So if you designed this convolution to have a certain frequency response, then here's an implementation of it, all right, in real time. Of course, there are other techniques for DSP. Sometimes you would rather use the Fourier transform explicitly to do your convolutions if you have a long enough buffer, okay? But sometimes you do it just directly like this if you're doing a short convolution. So what does that mean? An FIR filter, you have some finite length impulse response. So it's finite in length, and we would say that the order of this filter is order 3. So this is a third order FIR filter. By the way, the details of implementing these filters are not something I really care for you to memorize. Really, this showing how to implement the filters here is for your own edification, and also for so you can just see how all the concepts of Fourier transforms are coming together and making sense in these different applications. In other words, knowing what a 10th order FIR filter is not crucial for, most of filtering is beyond the scope of this class, I guess. And notice that this was you need n memory elements for order n. So basically n is the, and the length is n plus 1 of this filter, of the FIR filter. Right? It was a length 4 impulse response. And you needed n memory elements to implement it. Okay, now let's talk about how do you do an infinite impulse response. I mean, are we going to be able to do that with finite memory? What do you think? Is it implementable to do an infinite impulse response? Well, some of them are. Here's an example of a way to get an infinite impulse response that's fairly simple. So I'm going to do another block diagram. Let's say you have xn. And here what we're going to do, out comes yn. What I'm going to do with my memory is I'm going to actually hold on to the previous outputs and put them through delays. So hold them in memory. Whoops, let's make that longer. And they're going to be fed back and added to the input here. We're going to have some, I'm first going to maybe have some scaling on the input. Let me just call that A. Whoops, some amplifier here, according to whatever design I want. And then these get added. And everything gets added together out of here, but they're amplified to some desired value. So there should be an amplifier here too. So they're multiplied by some constants and added together. And finally, there's no addition there. It just goes here. Okay, so it's similar looking, but the design here, and I'll just call these are no longer directly the h values, but there's some constants, b0, b1, b2, okay? And the point here is that in terms of complexity of implementing, this is basically the same, right? You have 4 multiplications, you've got 3 memory elements, but what we're getting here is not going to be a finite impulse response. To see that, I mean, you could just trace through, put a delta function in, and what you'll find is that delta function immediately causes an output, okay, at time 0, but it also causes an output at time 1, okay, and an output at time 2 and an output at time 3, and each of those gets fed back as well. And so in most cases, this is going to just continually, it's never going to zero out. You'll keep getting feedback values indefinitely. It might die off, but it won't ever become exactly 0. So it's an infinite impulse response. Now, this may look like something you've never encountered, but I'm sure some of you have encountered this in software. When you want to track the value of something that's changing, and you want to do it in a smooth way, a common technique is you take the previous value and you average it, the previous value that you estimated it to be, and you average it with your new measurement of it. Okay. Yeah, I'm trying to think of a concrete example. Anyway, I won't brainstorm right now. But you've probably encountered this, some of you, in code, and not realized it's a filter. It's an LTI filter, and it's of this form. It's using feedback. The value you estimated it to be last time. In that case, in the simplest implementation, you just have one delay element. You just look at the previous estimate of it, average it with your new incoming estimate, and make that your new output. Okay. This and the impulse response of this is infinite. So this gives you other designs. Now, really, what you often do. Notice here again, we would say this is order 3. It's a third order IIR filter. Now, often you combine both. So you do both FIR and IIR together. It gives you some parameters, some flexibility in how you design the frequency response. So for IIR, use the memory to store the past outputs. Okay. Now let's just say, how would you actually, say you have a given frequency response in mind and you want to design an FIR filter. Here's one FIR, one possible design method that's sometimes used for designing an FIR filter given a frequency response. Let's just say the frequency response we want is a low-pass filter, an ideal low-pass filter. We want to make an FIR filter for it. So let's do this. Create ideal low-pass filter. Now, we won't really be able to implement an ideal low-pass filter, but one method would be start with an ideal low-pass filter. So this is going to be a discrete time filter. So let's do a little aside and say, well, we need to know what is the discrete time ideal low-pass filter. I think we already know this. Fourier transform pairs. Let's look at this. We know in continuous time, that we have this relationship between sinc and rect. Okay? And the low-pass filter is a rect in frequency, so it's sinc in time. Let's check what happens in discrete time, see if we still have that relationship. So if you have a sinc of, let's say, some cutoff frequency fc. Actually, for the regular sinc, the cutoff frequency is a half. So let's say it's 2fc here times n. Okay, so if n were a t, this would be a low-pass filter with cutoff frequency fc. All right. If you do a Fourier transform of this, what do we get, do you think, for discrete time? I should put brackets around it. That's what we like for discrete time. Okay, turns out it is the same. You still get the ideal low-pass filter, assuming fc is less than a half. Okay, so because remember, in discrete time, you only really go up to a half in frequency. Then it's periodic after that. So we would actually get the ideal low-pass filter from that sinc. Nothing changes going to discrete time, except that it's actually periodic. So really, this is the Fourier transform. Okay, it repeats. Right? It has to. In fact, we could have known that, because you could have said, take a continuous time sinc and sample it. Right? And the continuous time sinc is band limited, because the rect is bounded. So the continuous time sinc will, when you sample it, you won't get any aliasing. They'll just be separated. Nothing weird happens, unless fc was too big. Okay. Now, what about this, though? What if you do something like a rect of some scaled thing of an n over like a some n here, some width, cap n. Okay. Now you saw in your homework that you already did this, right? In your homework, you took a rect in discrete time, and you did the Fourier transform. And what did you get? Did you get sinc? So you got actually something that was a sine over sine. Okay, this was like sine of pi f, and this up here was sine of, depended on n. Had something to do with n. It was like n pi f or something. We'll look in the homework. So you actually get something that's sort of sinc-like. If you were to plot it, it's sinc-like, but it's not exactly sinc. So a word of caution that if you take what you know in continuous time to discrete time, you better check that it still holds. But what we want is the low-pass filter. That's this top one. So we still have that in time, this is actually a sampled sinc. Okay, so let's get back to our filter design. What we have here is, here's n, and we have some sampled sinc. That's our ideal low-pass filter. Not drawing it very symmetric. Let's see, 1, 2, oh, okay. Okay, so there's our sinc. Ideally, this would keep going forever, and that would be the impulse response we use, but we need a finite impulse response. So then you might say, step 2, I'm going to truncate this in time so that it becomes finite. All right? So that means I'm going to cut it off because I only have a certain length of a FIR filter I get to make. I'm going to make everything 0 out there. And I can do that convolution. Okay. Now, there may be one more constraint. So this method is sort of start with the ideal and then start adding your constraints. Here's another constraint. You might have to be real time, meaning causal. So maybe you're looking at a real time process. Maybe you're not. But if it is real time, then in fact you would have to be causal. So you can't, notice in this block diagram, I can't use memory to look at the future of x. So the impulse response has to be causal. All right. So then what you would do is just delay. So this would mean make it causal with a delay. So you take our, here's our, this was 0 in this picture. And we would instead take this whole sequence, this impulse response, shift it this way in time so that this becomes 0 and this becomes, whatever n. This is the n plus 1 for the order of our filter. Okay. Great. So now so then what we would want to understand is what do we now have? We started with an ideal low pass filter, but we now have something we're implementing that's not exactly what we intended. So how did it change when we did these steps, like truncating? And to understand that, I think some of you might be able to guess what this is going to do in the frequency domain. So we started with frequencies. Here's 0, here's a half. We started with something that was an ideal low-pass filter, and it repeats, right? And how should we interpret this truncation? So it was mentioned last time when we were doing a different signal. We had a signal that was on and then off. And someone said, so what we've essentially done is we've zeroed out everything out here. So you can interpret this as multiplication by a rect. Okay, we've taken our original signal, we've multiplied it by a rect, which means in frequency we are convolving with this sinc. The discrete time sinc, in fact, because it's multiplication in discrete time. So it's actually the sine over sine version of the sinc, but not too important. So we're doing a convolution with the sinc when we truncate the signal. So that means the result is we don't have a perfect low-pass filter. We have something, you can imagine what happens when you convolve a rect with a sinc. The sinc hopefully is quite narrow because we've taken a long enough window, let's hope. Then it's going to be something like this. It's gonna overshoot here and undershoot there, something like that. So it's no longer the ideal low-pass filter. So this is what we end up implementing. What does the time delay do to this filter if we have to make it real time? What does that do in the frequency domain? So this was 2, and what does 3 do to our filter? You multiply by a complex exponential, which means you only affected the phase. This first process, by symmetry, so what's the phase of our ideal low-pass filter? It's 0. Okay? That when you do this truncation, if it's symmetric, you still have a 0 phase object. Okay? So what that means is this adds a linear phase. So a time delay adds just a linear phase to our filter. Okay, it's no longer a 0 phase filter. Okay, let me just mention this was one method of designing an FIR filter. You can approach this design, for example, by there's some methods of directly optimizing the parameters of your filter. So suppose you say, I'm going to do an order n FIR filter or an order n IIR filter, or maybe you're doing this combination. People call these ARMA filters, autoregressive moving average filters. But whatever, you have some parameters to fit. You can actually just fit this as a direct optimization problem. Optimize those parameters to match your frequency response as closely as possible. You're going to have some error, but you can minimize the total error. And there are many techniques. If you take a DSP class, you'll learn some of these techniques. Okay. Now let's look at a continuous time filter here. Change pace a little bit. All right. So now I'm going to draw a circuit diagram here. And some of you have done circuits and some haven't. And that's okay. We will explain what we mean here. So you have some voltage in coming here, you have voltage out here, and you have a couple more elements, resistor and capacitor. And this is ground. Ground is just meant to represent 0 volts. Okay, and I'm going to actually label some of these things to make the example specific. This is 2.5 millihenry. This is 100 ohms. And this is 1 microfarad. Okay, so you have 3 components connected together in this way. And you have a voltage coming in that's your input signal. And you're measuring the voltage on this node. And we're going to treat that as an output signal. So this is a system that has an input and an output that are both functions of time. And in fact, this is an LTI system because all of these components are linear time invariant. Now let me introduce what the components are. So you have these ideal passive components. Here is what we're using for this system. They're passive because they don't have anything like transistors that can amplify. So you have these 3 circuit elements. You have an inductor, a capacitor, and resistor. Now, if you took circuits last semester, you certainly saw things of this nature. Okay, maybe you built some. And the resistor is maybe the easiest to understand. The resistor is, there's a relationship between, for each of these, there's a relationship between the voltage differential across the device and the current going through the device. Okay, and I'll explain that relationship right here. For resistors, it's the simplest. The voltage, VT, and that means the voltage difference measured from across the 2 terminals, that is directly proportional to the current going through. And the constant of proportionality, we just call that R, and we call that the resistance. Okay. For a capacitor, and so this is drawn like that. For a capacitor, you have a relationship, proportionality between the derivative of the voltage and the current. And of course, there's another constant here. We'll call that C. It goes there. That tells you the proportionality here. That's the capacitance. And of course, this is drawn like this. And finally, for the inductor, you've got, now you have a relationship between the voltage and the derivative of the current. Derivative on the other side. And we have L here as the inductance. Now, the pictures are meant to represent sort of what they do. The resistor just kind of prevents current from flowing, you can think of. But the capacitor is actually built, one way to build it is with parallel plates close together. And what happens is no charge actually can pass through the capacitor, but you can get current to flow in one side, and it builds up a voltage that pushes with force the charge on the other plate, and it'll move off. And if you don't know there's a plate in between, you think current went through. It didn't really go through. It's like a dam. It's like a reservoir. It went in one side and stopped, and that caused some current to come off the other side. Okay. The reason it behaves like it does is after a while it builds up charge, and it can no longer take any new current unless you push harder with a harder voltage. So really, it's the integral of the current that went through tells you how much total charge there is there. And that total charge is going to cause a voltage. So that's why you have if you take an integral here, you'll see the integral of the current is the voltage. Okay. The inductor is like a coil, and because it causes because current causes electromagnetic fields, then then changes in currents through this coil are resisted by the coil. So the coil likes to have the current stay at a constant speed. If you attempt to change it, it's sort of like a gyroscope. It doesn't want to move. Okay. Anyway, the point is this. If we wanted to know what does this LTI system do, we might want to understand what does it do in the frequency domain. Here's one method for solving that. first of all, notice that we have the way you attack these circuits is you define equations over their currents and their voltages. Okay, I'm not going to do that step, but you can define that every node has to, the same amount of current in has to equal the current out of every node. That gives you some equations. And we have these equations that govern the current and the voltage relationship. And when you just write out all these equations, you find out it's a well-defined system. But it's a differential equation because you have all these derivatives in there. Okay, so what you would do here is you solve the differential equation. This is one method. Let me show what that might be like. So I actually have calculated out the so-called step response of this. And I have a graph of it. Okay, so for this particular system, if you apply voltage 1 at time, let's bring it up here. You apply voltage 1 at time 0, and just let it stay on. So the voltage was 0, and all of a sudden you apply voltage 1. Current starts flowing, but the voltage here follows this path. It ramps up, overshoots. It overshoots because of this inductor. Then it settles back down to 1 volt. Eventually stops at 1 volt. Okay, so this is the step response of this system. Now, from this, we can calculate an impulse response. And you'll see later the relationship between the step response and the impulse response. So the step response, by the way, in formula as an equation, when you solve the differential equation, you get something like this. Okay, so that was the step response of the system. And the impulse response, it turns out, is just a derivative of the step response. Okay, so we get h of t for this system equals, whoops, yeah. Okay, minus 400 million t e to the negative 20,000 t u of t. Okay, so here's some formula. I didn't plot it, but this is the impulse response of this system. Of course, what we really care about is understanding what happens in the frequency domain. So we could do h of f by taking a Fourier transform of that step response. All right, and I've done that for you, and you get something like this. 40,000 over 20,000 plus I 2 pi f minus 400 million over 20,000 plus I 2 pi f all squared. Okay, and we can combine this into one fraction, and you get 1 plus I 2 pi 10 to the negative 4f over 1 plus I pi 10 to the minus 4f squared. Okay, so here is our frequency response. Now, if we do a magnitude and phase of this, we would get that the magnitude of h of f is going to be the absolute value of the top divided by the absolute value of the bottom. The magnitude of the top divided by the magnitude of the bottom, and that's just going to be this. Okay, and how do I do that, by the way? How do I calculate the magnitude of the top? Yeah, so exactly. So you can think of it as rectangular coordinates, or you can just say multiply by its conjugate. Right? It's complex. Multiply by its conjugate and take a square root. Okay, but you're right. That's just going to be the RMS, the distance of this vector as real and imaginary parts. Okay, and the phase we can get like this. remember we have formula for phase. But again, there's an easy way to calculate phase, and there's a hard way. The hard way is often just plug in the entire function into your formula. The easy way is to say, well, at least we know that phases of fractions subtract. We can just calculate the phase of the top minus the phase of the bottom. That will save a lot of effort if you compute that way. Just like we did here, the magnitude, we just do the magnitude of the top divided by the magnitude of the bottom. All right. But the point is, I want to plot now the magnitude of h of f. Here's frequency, and here's the all right. Let's say this is 1 in the middle. So the magnitude of h of f actually looks like this. It's kind of flat, bumps up, and then it comes down like this. Okay, and this resonant point here is at, you can calculate it out, 3.2 kilohertz. So what that means is what we've designed here is a circuit that actually resonates. In fact, if frequencies at 3.2 kilohertz don't get attenuated like everything else does. Okay, so that resonates, whereas other frequencies like high frequencies get removed. They don't pass through here because that inductor stops them. So this gives us a very nice way to understand. The frequency domain gives us a very nice way to understand this circuit. It has a transfer function. It's designed to resonate at a certain frequency. Now, all this process of solving the differential equation and going through this, what I'm going to show you in the future, next week, is that we're going to learn the Laplace transform, and we'll see that we can solve these differential equations very simply. It's much easier than I made it look here. We can get the frequency response of a system like this immediately with hardly any effort. Okay, so that's going to be fun. In fact, you can kind of get a hint at how it's going to work by looking at this. You can get a hint at how it's going to work. Oh, you know what? By using the Fourier transform, but I'm going to save that till later because I have to give you a formula for your problem set, I think. Okay, so there's one more thing. Actually, I can fit this in. Yeah, one more thing, and this is called group delay. So I won't show you the easy way to attack that. We'll do that when we get to Laplace transforms. Okay, group delay, and that is how does the phase of how does the phase affect a filter, right? So a filter has a frequency response that affects both magnitude and phase. And often we might think only about how the magnitude is affected. But let's look at how what does the effect of the phase of a filter have? Okay, so we already talked about phase of like a long signal, that it has all the timing information. But filters often have relatively short impulse responses. So what does the effect of phase have? There's something called group delay that says, based on the phase, and maybe next time I'll derive it better. I intended to kind of approach it a little more slowly. But let me just give you a formula here for group delay, and we'll try to make some sense of it. It says that if you take the derivative of the phase, so group delay equals negative 1 over 2 pi times the derivative of the phase, let's say ddf, of the phase of the filter. So this group delay is a function of frequency, right? If you take a derivative, you still have a function of frequency. It says that for different frequencies, you experience different so-called group delay. And in fact, you'll find that this group delay is going to be the more relevant. It's going to really tell you how much frequencies in those ranges get delayed. I have an example here in MATLAB to kind of solidify this. So let's say I have a filter here. Figure 1 shows I've actually designed a filter that has this frequency response. I've plotted the magnitude of the frequency response only for positive frequencies. It's a real filter, so it's the same. It's symmetric for negative frequencies. So for positive frequencies, this And here's a log magnitude. So we see that frequencies 5 and 10 will be passed through without much change. Other frequencies, this is a log scale, so they'll be actually mostly eliminated from the output. The phase of this filter is plotted below. And you might not know how to interpret what is that going to do to your signal, but we'll see in a minute. I'm going to put this input that I've designed into this filter, and then in a moment I'm going to plot what comes out. Okay? Now this input, we can see in my code, I just have 3 sinusoids added together. This input is right here. It's 3 sinusoids, one at frequency 5, one at frequency 10, one at frequency 7. And then I've multiplied some envelope that makes it not just go on forever. So let's see. So I've multiplied some envelope so it kind of starts and stops. Okay? But it's basically 3 different frequencies. And we know it's got a frequency 5 and a frequency 10. Those should not be affected much by the filter in terms of magnitude. The frequency 7 should be basically eliminated. Okay? But there's one thing we can anticipate from the phase. Notice that the derivatives of the phase are different for the 5 frequency and the 10. I designed those to be different. So according to our calculation, these should have different group delays. The part of the signal that has frequency 10 should experience a larger delay than the part with frequency 5. We could even anticipate what the delay is if we calculated that derivative. So now what I'll do is I'll remove this comment from my code so we can see what the output looks like. Okay, so notice it's exactly what we said. You get 2 sinusoids out. All right, the 7 got eliminated. And the 5 frequency gets delayed a little because the slope's only a little. The 10 frequency gets delayed a lot. Okay, so magically we see this group delay coming to life here. I can justify to you in the next lecture why this group delay works this way. But I have one more part of this demo. Okay, I'm recording a little bit extra onto this lecture. We have some lectures canceled coming up, and I don't want to get behind. So first I'll start where the recording cut out for some reason at the very end of the demo. We have 2 demos in this file that I've created. You just saw the one where we designed a filter to cause different group delays to different frequencies, and we illustrated that by having an input composed of different frequencies that each experienced a different delay through the filter. The next demo here is just to kind of understand why filtering why group delay works this way, why the derivative of the phase causes a delay in the envelope of the sound. By envelope of the sound, I mean if your signal, it doesn't have to be sound, if your signal is concentrated at some location in time or space, then group delay will tell you how that packet of concentrated energy will be delayed forward or backwards in time, depending on its frequency. Now, I'm going to contrast group delay and phase delay here. Phase delay just means adding a phase into your signal. So a filter can certainly change the phase of certain frequencies. So we'll go to experiment 2, and I'll start with changing the phase. What I have here is a signal composed of 3 sinusoids very close in frequency. So here are we have amplitudes and frequencies, 5, 5.2, 5.4. We sample, the sampling doesn't matter here. And we have just some arbitrary phase to begin with, but what I'm going to do to illustrate what happens if the phase changes, first I'm going to show if the phase of all 3 sinusoids changes together, we get what some would call a phase delay, and you'll see that illustrated here. So I'm just going to render cosines with those amplitudes and phases defined by those vectors, but additionally it's going to then the animation will then add a phase to each of these sinusoids. So here's what we get. Okay, notice that, first of all, forget the animation for a minute. Notice that these 3 sinusoids close in frequency look kind of like one sinusoid that follows some sort of envelope. We know that happens when you have frequencies close together. They sort of interfere and they create this envelope. I want you to pay attention to the fact that right now that envelope is not moving. We're changing the phases, and so the phase delay is causing these wavefronts to move, but the envelope is not changing as I change all 3 sinusoids phase together. Now, let's flip this switch here. Now what I'm going to do is I'm going to make the overall phase is not going to change of the sinusoids, but relative to each other, we'll get a change. So one of them, I've got 3 frequencies involved here, so the 5 frequency is going to go up in phase. The 5.4 frequency will go down in phase. 5.2 will stay the same. Okay, notice what's happening. The wavefronts aren't moving, but the envelope is moving. So group delay really has to do with this difference of phases of nearby frequencies. And this example is here to show you that by changing the relative phase, we get the envelope to move. And group delay is concerned with where these energy pockets are located. It's usually the more relevant delay when you're talking about a filter. Okay, now let's go back to discussing why group delay works the way that it does. So, first consider the frequency response of a filter. Oh, it won't go down, huh? All right. So, consider a filter with an arbitrary, Okay, so here's the frequency response of a filter, and it has both magnitude and phase. I'm just going to draw it as if it's one-dimensional, something like this. Oh, it's ugly. Let's use the one we had from our continuous time thing. It kind of peaked up there, went kind of like that. Okay, now, suppose that we consider narrowband parts of this filter. In other words, this filter affects all frequencies of a signal, but let's divide it up into segments, narrow segments, and assume that, and see what happens if a signal comes in that only has frequency components concentrated in a narrow range. All right? So if that happens, then the filter's frequency response in that range is all that matters for that signal. Right? So let me get some colors here. For example, if a signal only has frequency content in that range of frequencies, then this is the only part of the filter that matters. Nothing else matters. All right? We can put make this nice and colorful. So we divide up our filter this way. And notice then that if we want to know how this filter affects a particular band, like let's say here's a particular frequency and we have a signal that's only in that range, then we might as well assume whatever we want for the rest of the frequency band. So we could keep that part intact and assume that the rest is however we want it to be. It's not going to matter. Okay. But if this band is small enough, then this little rectangle could be approximated by a Taylor series expansion. In other words, what we could do is approximate that the magnitude is constant, okay, and that the phase is not constant, but let's do a first-order Taylor approximation. So replace with Taylor expansion. So that's going to look something like this. We'll say that HK for the kth frequency band of F is approximately the magnitude of H at that frequency F, all right, times the phase at that frequency, e to the I phase of H of F. But we're going to put in one more term of the Taylor expansion into the phase because we care if it's got a derivative up there. F minus the frequency minus that constant phase times the derivative of the phase. Now this notation, I mean derivative with respect to frequency of the phase, not the phase of the derivative of H. In fact, let me just replace it so there's no confusion. D df phase H of F. Okay. Now what does that mean? That means that the output here lie in that frequency band. Part of the signal that lived in that frequency band is going to be approximately the input that was in that frequency band times the, now, if I combine these two parts together here, that is just the actual value of h of f, okay, magnitude and phase, but multiplied by well, let me say it equals that, right? Approximately, which approximately equals, like we said, the value of h of f times e to the I d df of the phase. Okay. Now, notice that this looks like a delay by negative 1 over 2 pi. Because we have a delay rule, right? When you delay a signal, derivative. When you delay a signal, you multiply it by a complex exponential in frequency. Okay, so this is an explanation for why the derivative becomes the phase shift. Oh, this should have an f here. No, I'm not explaining this very well. There's an f minus cap f. So what we have is times f, and the cap f part, oh no, this is still, this is what I want to do. I'm going to go back in time here. Okay, so using this Taylor expansion, then we can say that the output of, in that kth band of frequencies, okay, is going to approximately equal the input that lived in that range of frequencies times this filter, this Taylor expansion, or the filter in that frequency band, right? But we've approximated that with the Taylor expansion. So that's going to be x k of f. And that's going to be, now we have h of f. E, I'm going to separate this exponent into two parts. The phase, the magnitude of h of f. The phase of h of f. And I'm going to also include the constant f here. So it'll be minus capital F times the derivative of the phase, evaluated it at capital F. So it's ddf of that phase evaluated at F equals capital F. Okay, but then we've got the last part here. Let's do this. Plus same derivative, ddf times f. That's evaluated at f equals cap f times little f. I don't like drawing that so much. Go back in time again. And this derivative is evaluated at f equals this constant frequency that represents the bin, cap f. Okay, so let's give this thing a name. Let's just call that d of f. maybe think of that as delay. Okay? For simplicity, because I'm going to end up writing this too many times and it'll get annoying. Okay, so that means that if we want to know what the output looks like concentrated in that frequency band, that's going to be the product, because it's you apply the filter, of the input in that frequency band times this times our frequency response. Now this frequency response has been approximated closely for that frequency band, so we can use that Taylor expansion and say that's the input times the magnitude of h of f, e to the I, and here we'll have the phase of h of f, and then let's split out that difference, f minus cap f. So we get d of f, remember that's our derivative, times cap f. Sorry, we'll put a minus in front of there. Plus d of f times little f. Now I want to separate out this last part. I'm just going to write a separate exponential term to make it clear that this is a product. So this is I d of f times f. Okay, great. Except for this d, sorry, this should be a cap f because we're evaluating it at a particular constant frequency. So I'm going to replace that everywhere here. So f minus d of cap f times f. Don't want to make it look like this is a... For that whole frequency band, we're just approximating the derivative of the center frequency. Okay, so the point is this. This whole thing here is just h of f. This is just some constant phase tacked onto h of f. So we can say this equals x times h of f times some constant phase term. E to the negative d of f times f, okay, this whole thing, times e to the I constant, but here f is little f. It's the frequency. In other words, it's varying. So now what can we identify? Well, this is just, you basically just multiply the magnitude of x by this constant number. But we know that that when you multiply by a complex exponential, that's a delay. Delay by what? By negative 1 over 2 pi d of f. Okay, so why is it a delay? Well, we have a delay rule. We know if you delay a signal, you multiply by a complex exponential in frequency. So this should give an explanation of why the derivative of the phase becomes a delay. I just wanted to connect that with a delay in the signal. If you only looked at a narrowband signal, then the Taylor series approximation is good. And the Taylor series approximation says you have a linear phase shift. Linear phase shifts are delays. Okay. Let's now, we're going to revisit that circuit example. But before we get there, let me just make one quick comment. When we did this FIR filter design, we went through these steps. We said one method was to create an ideal low-pass filter, then truncate it, and then maybe delay it if you need it to be real-time. We looked at what does that do to the frequency domain. You don't end up with an ideal low-pass filter. Well, remember that the reason you don't have an ideal low-pass filter is the windowing. The truncating was a windowing, and that meant you multiplied by a rect in time, which was a convolution with sinc in frequency. Well, there are ways of trying to mitigate this effect, and this is referred to as windowing in DSP design. Instead of multiplying by a rect, you could come up with some other function that also is finite in duration. Usually it'll look something like it'll kind of get rid of the edges a little bit. Okay. There's a lot of window functions that you use instead of rect. Multiply your ideal low-pass filter by this new window. It'll still convert it to an FIR filter because it's still finite in length. But in the frequency domain, you'll be convolving with something else, and you can design that window to give you something that maybe is a little sharper. I mean, whatever you're looking for. Maybe it has smaller overshoot, or maybe it's, usually it's like the overshoot that they want to get rid of, or whatever. So you have various window functions that you can choose instead of just doing a rect. Okay. Great. So let's go back to our circuit example here. I said that there would be other ways of getting to the frequency response, simpler ways. And the truth is, we'll come across these using the Laplace transform, which we do next week. We'll be much more capable of handling this in the general setting. But because this specific example has only passive components, then we know that this system is a stable system. And in fact, the Fourier transform is going to be just fine for calculating the frequency response here. So let's do that method. So what we're going to notice is these equations we have for inductor. I'll come back here to these equations. The equations we have for inductor, resistor, and capacitor can all be converted to, we can rewrite them in the frequency domain. In other words, take a Fourier transform of both sides of these equations, and we'll see that becomes another expression. Derivatives, we have a derivative rule. So we know that V of f equals L times the derivative of I when you take the Fourier transform is just going to be I of f times I to pi f. Okay, so it's just a multiplication there. And the other rules will be similar. And there's a better way to write this. We'll write that we now have a ratio of V of f over I of f equals I to pi f L. Or let's put the L first. I to pi L f. Okay, so that's our rule for inductors. And then for capacitor, we have also that there's a ratio between V and I, but this time it equals 1 over I to pi CF. And then finally, let's move this a little bit. And then finally for the resistor, it's going to be very straightforward. We just have that V of f over I of f equals R. Okay, so now what we found is after taking Fourier transforms, all three of these components behave in what you can consider to be the same way. They all behave like a resistor. The resistor, you could have written, since there were no derivatives involved, even in the time domain, V over I equals R. And now we see that inductors and capacitors also behave that same way. The V over I equals some function. Now it's a function of f. Okay, but it's sort of a resistance that's frequency dependent, and that could be imaginary. All right, you can think of it that way. Now there's a name for these formulas. This is called impedance. And if you've studied circuits, you've dealt with impedances, and you've seen how you can use impedance to calculate the frequency response of a circuit. I hope that now, with our understanding of the Fourier transform, we see exactly where this is derived from. All we've done is taken Fourier transforms of these equations, and we now have a new set of equations in the frequency domain. So you can go solve the, so you can go take all of the equations you have from this circuit. Now I'm going to show you what we didn't do explicitly when we said that the differential equation needs to be solved. The way that you actually go about doing the derivation we've already done, but doing it the simple way, is you say, okay, well, we know we have some current, I, going through, if any current that goes through any one of these goes through all three. Okay, so it's a constant function of time. I mean, it's a function of time that doesn't depend on which component you're looking at. Now, we're going to label another voltage here. Let's label this voltage just to be V1. So it's V1 of t or of f, whichever domain we're looking. Okay, so okay, so now what we do is we say we have a system of equations of this form. we have that V in of f equals V1 of f plus the voltage across the, V out minus V1 of f, right, plus the voltage across that inductor, V in of f minus V out. So far, what I've written is trivial. Don't have to know anything to know this equation, but now we can go substituting these in. Okay, so V1 was the voltage across that final capacitor. And we know that is going to be I of f times 1 over I 2 pi CF, okay? Plus, now the voltage across the resistor is just I of f times the resistance, plus the voltage across the inductor, I of f times I 2 pi f, okay? Now V out of f is just these first two. It's just the voltage across the capacitor and the resistor. By the way, that could be simplified. I could factor out the I of f. And what I have here are the sum of these impedances times I of f. Okay, so that's what the voltage in equals. Now the voltage out is similar, but it just has the first two. I 2 pi CF plus R, I of f. Okay? And what we want to know is the frequency response of the system. But by definition of the multiplication rule of convolution says that V in times the frequency response equals V out in frequency, right? So that means that this ratio V out of f over V in of f is exactly the frequency response. But we can just divide these, the i's cancel, and we get that it's 1 over I 2 pi CF plus R over 1 over I 2 pi CF plus R plus I 2 pi LF. There you go. We've effectively solved the differential equation. We've done it in the frequency domain, which actually is what we cared about. So going straight to the frequency domain using this technique is so easy. We never had to do a Fourier transform. We never had to explicitly go solve the solution to the differential equation in time. If you plug in the R, C, and L, you'll get the formula I gave above for the frequency response, which was right there. Okay. Now, if you wanted to go get this in the time domain, you could do an inverse Fourier transform and figure out what the solution to this differential equation is in the time domain. So next week, we will actually solve differential equations, and we'll do them in a very simple way, just like this. But we'll use the Laplace transform because there are cases where that gives us sufficient generality that we need to actually do these differential equations. Okay. So next, let's do one last short topic here. If we probe, I want to talk about probing an LTI system. Again, this is sort of an exercise of everything all the properties we've learned so far about LTI systems and Fourier transforms. Suppose for a minute, consider that you have an LTI system and you want to learn its impulse response. Okay, you want to know what is h of t. Well, one way to do it is tap the input. Put a delta function at the input, right? By definition, what comes out is h of t. So there you learn the impulse response. However, in reality, how do you create a delta function? And maybe you have some constraints. You can't hit your system hard enough to even simulate a delta function. Okay, so what other ways are there that we can learn h of t? Well, let me give an example of a way that you might try. And let's talk about whether it works or not. What if I put sinc of t in? So somehow say I could generate a sinc, put it into my LTI system, and I'm wondering, have I now learned sufficiently what this, what the impulse response is of this LTI system, and thus, if I know the impulse response, I know what this system will do to any input. All right. Well, What I'm going to get out is the convolution, right? I'm going to get out h of t convolved with sinc of t. And is that enough? Can I recover h of t? Well, from first principles, you could realize this is not going to be enough. This does not recover high frequencies, right? So it does not measure all frequencies. If we think about it in the frequency domain, it'll make the most sense. In the frequency domain, we have h of f. Here's some h of f. And the output we measure, we don't know h of f, but we put a sinc in, which is a rectangle in the frequency domain. And we get out their product. By getting out their product, that means we only get out something that looks like this. Well, that's going to teach us what h of f is for low frequencies. We can recover h of f for low frequencies from that, right? But we know nothing about what the high frequencies were. Okay, so sinc of t is not a sufficient probe. Maybe if you made the frequency, maybe if you condense sinc of t to a very short time duration, then it looks kind of like a delta function. And you said, well, I'm at least going to learn low frequencies of my system up to some very high frequency. Maybe that's good enough for you. But in general, you would need to probe with some input that has non-zero Fourier transform for all frequencies. So here's an example of one that would actually work. If you did this as your input, okay, take the Fourier transform of that, and you'll see it's non-zero everywhere. So that actually would tell you all frequencies, the entire characterization of your system. Essentially, what you want to do to recover h of t is you want to take this output and filter it through the inverse associated with the input signal. But sinc of t does not have an inverse because it has frequencies that are zero, that have zero amplitude. Okay, delta does have an inverse, it's just delta. And this e to the negative t u of t does have an inverse. Okay, so let's talk about this a little more practically. So here the problem is the Fourier transform had zero regions. And this here was okay. So essentially, whatever signal you put in to probe the system, it better probe all frequencies of the system. Okay, we would recover h of t in general by saying, by doing the inverse, inverse Fourier transform of h of f, which equals inverse Fourier transform of the output that we measured over the input, which we knew because we put it in. All right, so that should not be zero. Okay, now in reality, what might you do? Okay, you can try to put a delta function in. That might not be very physically realizable. You could scan all frequencies. You could try to build your knowledge of h of f by putting a sinusoid in. Of course, one sinusoid is a very bad probe. It's only going to tell you the value of h of f at that frequency, right? But you could get a function generator that generates sinusoids, and you could plug it up to your LTI system and just sweep across all frequencies. Take a whole bunch of measurements that helps you reconstruct h of f. That's pretty common. Here's another way. Look at this unit step response, and we saw that when we were looking at the circuit above. I told you what the unit step response was for that particular circuit. But in general, you define this to be what comes out of your system when you put in u of t rather than delta of t. So that's the unit step response rather than the impulse response. I'll represent this with a tilde over h. So it's not the impulse response. This is the step response. All right. So h tilde t equals h of u rather than h of delta. All right. Now, how is this related? I already mentioned before it's related through a derivative relationship, but let's derive that. It's very simple. So how is it related to h of t? And here's how we'll see the relationship trivially. So notice that an integrator and a differentiator are inverses of each other. Okay. So if we put in anything here, x of t, then we get x of t back out. Okay, because these are inverse systems. Now what we want to do is actually put in delta of t here. So let's change that to delta of t. Then we'll get delta of t out. We always get the same thing in and out there. Now here's our LTI system, and we want to measure h of t, which is going to be the output if you put delta in. Okay. But these are all LTI systems, and therefore they commute. So I can, in fact, change the order. I can say if I put a delta function in here, keep the integral here, but switch the order of the LTI system and the differentiator. Okay, let me change that. Rather than just say LTI, since they're all LTI, let's call this H, capital H. Okay, so this is the same thing. I should still get h of t out. But notice, what do I have here? What's the integral of delta? That is u of t. Okay, then what comes out here? That's our h tilde of t. That's the unit step response. So now we see that this right here tells us that the derivative, that the unit impulse response equals the derivative of the step response. Okay. So the step response is actually a very practical way to measure a system. Put u of t in. That's easy to construct in reality, like for a circuit. Turn on the voltage. See what comes out. Take a derivative. That's your impulse response. There's one more thing I must mention. Just an FYI, because you might encounter these in your lifetime, and it's worth mentioning. They're not. It's not difficult, and these are Bode plots. Bode plot is a way of representing a Fourier transform, and it's particularly good if you have Fourier transforms of the form of the one I have above. So first of all, it's a continuous time thing. So if you have a continuous time frequency response, it's a way of plotting the frequency response in terms of log magnitude and phase. Okay, so of course it's common that you might want to plot it that way, but what the Bode plot does is it puts the frequency axis on a log scale as well. So it does it versus log f in both cases, and that's really what is different about a Bode plot versus what we've already seen about plotting the magnitude of phase. Now, why is this something worth pointing out? It's because when you make these, when you decide to plot it on these scales, you have some simplifications that allow you often to, by hand, plot a quite accurate representation of what the magnitude of phase will be. It's useful to be able to do that because it gives you intuition when you look at a formula of what the frequency response is without having to go to a computer and actually plot it. So let me show you how this works. First, we'll do it as a demonstration with the h of f above for the circuit. So in that case, we had h of f equaled 1 plus I 2 pi 10 to the negative 4 f. Okay, over this. All right. Now I actually gave you a plot of this by hand that was on a regular frequency scale, not a log frequency scale. So let's look at, now the point is, if it is quite common to have frequency responses, especially for circuits, that are of this form. You have a product of a bunch of terms that are binomials that have an f in them. Okay, we'll see as we study Laplace transforms, why this occurs so much and what we have a name for these types of frequency response functions. But anyway, let's just use this as an example. If it has this nice form, then the log of the magnitude simplifies in the following way. Notice that, of course, the log of this, the magnitude of this. So we said, we already said above that the magnitude was square root of 1 plus 2 pi 10 to the negative 4 f squared over this. And, okay, so that was the magnitude. So if we take a log of that, then we get 1/2 log of this, 1 plus 2 pi 10 to the negative 4 f squared, okay, plus or minus log of 1 plus. Okay, so we get that. Now, here's the key. When you add two things in a log, if you have a log of a sum, often a good approximation is that this is the log of the max of the two. Okay, because first of all, of course, it's bigger than the log of the max, so this is a lower bound. But it's also a pretty good approximation because if one of them dominates the other, if one of them is a lot bigger, then it's going to be close to just the larger one, the log of the larger one. So we'll use that approximation. We'll say that approximately equals 1/2 log of max of these two things, 1 and 2 pi 10 to the negative 4 f squared. And I won't, and of course then we would do the same thing here. Minus log max that and that. Oops. Okay, so that's the main approximation. Now, how come that helps? Well, because this becomes, notice that if 1 is the max, log of 1 is 0. And so what we can do is we can replace that and say that equals 1/2, and I can just by inspection say this is going to be the max of these two things. 0 and log of this second term. Now that simplifies the square, right? That becomes a 2 log of 2 pi 10 to the negative 4 f. Okay, good. So, and then it's minus, and then this is a similar type thing. Max of 0 and 2 log pi 10 to the negative 4 f. Okay, which means now that, notice that this here, this becomes a sum of a log f and a log of 2 pi 10 to the negative 4. Okay, so last simplification here, we have 1/2 max of 0 and of 2 log f, plus 2 log some constant here, 2 pi 10 to the negative 4. All right, minus something similar. Max 0, and it's again 2 log f minus plus 2 log. Plus 2 log of pi 10 to the negative 4. Okay. So remember that we said for the Bode plot, we plot log magnitude versus log f. Now we see the convenience of that because log f, because this is now just linear in log f. Log f, and here, and everything else is just constants. Or so really what we find is that we have a piecewise linear function here. So we can plot this easily. So here is log f. And we say that Well, up to some point, so we're going to have 0, the function, okay, so here's log f. Up to some point, so we're going to have two, this first thing is a max of two things. It's a max of the 0 function and another function that's linear in log f. In fact, that function is just going to be slope 2, and it's going to cross the origin at, this will be 2 log 2 pi 10 to the negative 4. All right. So really, the max of these is I'll draw in red. It's just these. Now the second term is going to be minus a max. So the second term will be some function, we'll be adding, taking into account the minus. It'll be something that is 0, and then when it reaches some high enough log f value, it comes down at the same slope, 2f. So really, all we have to know is where are these corner points in order to get a good plot. When we add these, the sum of these two things is going to be something like this. The result will be log f here, and it'll be something along this direction. Let's just arbitrarily put a 0 there. Of course, these are log frequencies, so negative is still relevant. It's going to be something like it reaches some corner point, goes up, slope of 2, reaches, let me make the slope of 2 a little less in my picture, hits the second corner point, and now it goes down, although notice something here. There was a half. I forgot to take into account the half. That half in front makes this thing a 1, and it makes this slope smaller than the second one. So the slope here was 1. And this slope is negative 2. Okay, so that means when it hits the second corner point, not only is it going to flatten out, it's going to start coming down at a slope of negative 1. Indefinitely, so it's going to keep going down. Okay, so the magic of the Bode plot, the reason that you learn to do it, is because when you get used to it, you're able to identify these corner points quite easily. And all you end up having to know from the formula is where are the corner points going to occur, which really has to do with for what frequency does 1 equal 2 pi 10 to the negative 4f. For what frequencies are these equal? Those are the corner points. And then you just need to know what are the slopes in between those corner points, which is also something, just has to do with the exponents up here. So you can become very good at quickly coming up with these plots so that you know what happens in the frequency domain. Here you see resonant frequency, right? Now we know, if you were good, just by looking at the formula, you'd immediately be able to figure out what the resonant frequency is. And you also would see that it's a low-pass filter. When log f gets high enough, it attenuates. And for low frequencies, which are this direction, low frequencies, it's going to be a constant 0. The log amplitude is 0. That does not mean the magnitude is 0. That's a log magnitude. So the magnitude is 1. So it just passes things through. So this does correspond with the picture I had up here. The only difference was in this picture, I did not, well, not this picture. In this picture, I don't have a log scale in either direction. Okay, but it should match up.